Okay, so we're going to start today's lesson on exponential and logs. Okay, so these are prior knowledge questions. Usually have a go at this, but in this case, we're going to move on. Look at the first bit of graphs and exponential functions. So we need to be familiar with some exponential functions. So for example, if y equals a to the power of x, where a is greater than 0. So for example, y equal to 2 to the power of x, or y equal to 5 to the power of x, and so on. And if we were to draw the graph, for example, of y equal to 2 to the power of x, so we'll put some x values in there. So if we go from -3, -2, -1, 0, 1, 2, 3, and work out the y value, bearing in mind 2 to the power of -3 is actually 1 over 2 to the power of 3, so that'll give us an 8. Next one will be a quarter, a half, 1, 2, 4, and 8. So what you see here is the graph, as x increases, is going up and up very quickly. So if we were to plot these points on the xy axis, we will see it looks something like this. So clearly this is a exponential graph. So what we say is any graph of a to the power of x, provided a is bigger than 0, will look something like this. What you see from here is all exponential, provided a is greater than 0, will go through this coordinate here, 0, 1.
Yeah.
So here's another two graphs. So if we had y equal to 3 to the power of x, it will go up very quickly. If we had y equal 1 to the power of 5x, it will go like this. As you can see on here, when x equals to 0, they all have this common point. They all pass through 0, 1, and they never go below 0. And if you notice that the either side of 0, 1, the biggest or smallest value, they switch. So above 0, 1, y equal to 3 to the power of x is the biggest value. Below 0, 1, it is the smallest, and so on. So here's another example. We have exponential graph going up, another one exponential decay. So the one that's decaying would be when a is less than 1. So for example, a half to the power of x will look something like that. And you see they both go to this common point, the coordinate 0, 1.
Yeah. Just keep cutting out sometimes, but it's fine. Can't plug in.
So half to the power of x, if you think about half, that's 2 to the power of -1. And so the graph of 2 to the power of -x.
Yeah.
So imagine you had £100 in your bank account and you are getting a very generous rate of 100% interest per year. Let's suppose we started off with £200, okay, and your bank manager says rather than give you 100% per year, what we'll do is we'll pay, we'll split it up into two payments of 50% for 1 year. So if we work that out, so it'll be 100 times, you're going to get two lots of 50%, so it'll be 100 times 1.5 squared. So it'll be 225. Yeah. So if we invest this example further, so if we start with £100 and we take one payment of 100%, we know that would be just £200. If you invest £100 and you took two payments, so you're getting 50% of every 6 months, and that will give you 225. If you split into 4 payments, so you got 25%, that gives you £244.14. Remember, this is just a compound percentage from your GCSE. So if we carried on with this table, you will see that there's a special number that's coming up, which is E. So what we say is if we take n payments, so we're dividing 100 by n, so we're splitting up our payments in very small chunks, we could write this as 1 plus 1 over n to the power of n equal to E. And the E number would be approximately 2.718. And just like pi, E goes on forever. Okay, it's an irrational number. So the larger the value of n gets, the better accuracy of e will be. So the value of e is irrational, just like pi. It also has another interesting property.
Yeah.
So if we look at the gradient functions of the exponential, so first let's look at y equal to x squared. So when you differentiate that, you get 2x. So this is the function y equal to x squared, and this is the gradient function.
Yeah.
So the gradient at this point is the same as the gradient here, the value of y value of this graph here. Okay.
Yeah.
Now, if we do the differentiation of a cubic, x cubed, if you differentiate, you get 3x squared. And if we want to work out the gradient of this point, we simply go to the graph and we read off the value. So that's the value of the gradient.
Yeah.
So now what we look at is this exponential 2 to the power of x. If you differentiate 2 to the power of x, and you're going to learn this in next year, so we don't need to worry about where this is coming from. This is A2 differentiation, and if we plot the graph, it looks something like this.
Yeah.
3 to the power of x. If you plot the graph, it looks something like this. So what you see is actually one of them is just below 2 to the power of x, and one is just above. So what happens from the first graph to the second? The lines have crossed. Therefore, there must be a value between 2 and 3 where the lines are equal. And surprise, surprise, so the line would be equal when it's actually y equal 2.718 to the power of x, which we know is just the Euler's value of e to the power of x. So
e is the value where they're equal.
Yeah, that's it. So if you differentiate e to the power of x, you're going to get e to the power of x. So that's the other interesting fact about this particular number. So we could conclude that if you differentiate e to the power of x, you just get e to the power of x. Because if you look at the function and if you look at the gradient function, they give exactly the same result. So if we have a function e to the power of x, then f dash x will be e to the power of x. But if we have a function e to the power of kx, then if you differentiate that, you simply differentiate the top, the kx. Now differentiation of kx is just k, so you bring that down. So you differentiate the top, you bring that down, so e to the power of kx, f dash x would be k e to the kx. So we've seen how to differentiate e to the 2x. You just differentiate the top, bring that down. A differentiation of e to the minus half x, you differentiate minus half x, so that gives you minus half, you bring that down. And differentiation of 3e to the 2x, you differentiate the top, which gives you 2 times by the 3, so 6e to the 2x. So now what we're going to do is just look at the transformation of e to the x. Now you would have covered the transformation chapter at some stage, which I think was earlier on the book. So now what you need to do is do the same thing what you've learned in transformation on chapter 4, but you're going to do it with the exponential. So if we look at e to the x graph, because it's 2.718, we know it's going to look something like this. So 2e to the x. So if we say this is the function f of x, then this would be 2f of x, because we multiplied the function by 2. And from transformation of graph, we know what we've done, we're doubling the y value. So it will look something like that. So my advice would be always try to write it in the function like f of x, then 2f of x, because then you could see what's going on.
Yeah. So I just got the translations up here, okay.
Yeah. So if we had, again, we're looking at e to the x graph. So if we had a function y equal e to the x plus 2, we know that this can be written as f of x plus 2. So this is just saying whatever the y values are, just add another 2 to it. So in this case, it's just going to be a translation in the y direction by 2. So your graph is going to be the same graph that's gone up 2. What's interesting here is your asymptote, which was y equal to 0. Your asymptote this time is going to be y equal to 2. So it's important in the graph you draw the asymptote line and write y equal to 2. And the other thing the examiners will be looking for is the intersection on the axis. So before it was 0, 1, now you've added another 2, so it'll be 0, 3. If we had y equal to minus e to the x, well, that's just the same as saying the function, but with a negative f of x. Now that's just a reflection. So if you have minus f of x, we know that this is a reflection on the x-axis. So we could straight away sketch that graph. Because if you're minusing the whole function, so this time if we had y equal e to the 2x, so the x has been replaced with 2x. So again, from your transformation skills, we know this is a stretch in the x direction with scale factor of a half. So our graph would look something like this. But we still have the common point 0, 1, because if you replace the x with 0, e to the 2 times 0 will be 0, and e to the 0 is 1. So they still go to the common point. What it is just going to rise quicker than the original one. If we had y equal e to the x plus 1, notice the whole power is x plus 1, and it's not ex plus 1 separately, it's e to the power of x plus 1. So this can be written as some function x plus 1. And we know that this, if it's inside the bracket, it affects the x, and it does the opposite. So it will be a translation in the negative x direction by 1 unit. So your graph is going to go left this way, okay, and then we're going to replace x with 0. So if we replace x with 0, we will get this gives us e to the power of 1. Okay, so we write down the y-interception as 0e. Okay, so now if we look at this one, y equal 10 e to the minus x. So the graph will go e to the minus x, but the y value is 10 times as big. So this is the original graph. Minus, remember e to the minus, the graph will be going like this. It's going to be reflection in the y-axis, and we just need to make it 10 times bigger. So the y value here, which was 0, 1, would be 0, 10 now. And let's have a look at this one. Y equals 3 plus 4 e to the power of 0.5x. So we're going to do it in stages. So if we think about e to the 0.5x, we know it will look like something like this. And then we're timesing it by 4, so that is affecting the y value. So it's going to go through 0, 4. And now we're adding another 3 to it. So the whole thing is going to go up by 3 more points. So our y coordinate is going to be 0, 7. The y-intercept will be 0, 7. So this is what our graph would look like. And it's important at this stage to also write down the asymptote. So why don't you pause the video and write down what you think the horizontal asymptote would be. So you simply just draw a dotted line here and you write down